Now moving on, before establishing the equivalence between the definition of limit superior given in Tao and Bartle and Schreiber, I want to address a small issue. Yeah. In the previous video, I had written 1 over here instead of infinity. So please rectify that. Then this is infinity, which is obvious because this is a sequence running from 1 to infinity. So let's now dive into the definition of limit superior given in Bartle. As Bartle states, let xn be a bounded sequence of real numbers. Then the limit superior of xn is the infimum of the set capital V of those small v's, where small v's are elements of the capital V, such that V is less than xn for at most a finite number of n belonging to the set of natural numbers. So this definition is quite dense and convoluted. So we will try to simplify it as much as possible. So what it essentially wants to convey is that we are looking for a sequence, for a bounded sequence of real numbers. We were looking for those kind of elements which are less than xn for all n belonging to some finite set S, where S is a subset of the set of natural numbers, right? For example, let xn be a given sequence, and then if there exists some real number such that real number v, the v is less than x1, x4 and x7 only, which implies that v must be greater than equal to xn for all n other than 1, 4 and 7. That is, this inequality is satisfied for every other index other than 1, 4 and 7. So you might be getting the idea what kind of elements we're looking for. I mean, what kind of set capital V is. So yeah, to develop, to establish the equivalence, let me just crop this. Yeah. So what we want to prove is that limsup of xn, which was shown to be equal to limit of this sequence xn plus, which was shown to be equal to infimum of xn plus, this will be equal to infimum of v. So this is the result that we are concerned with, what we are trying to prove right now. So the proof goes something like this. Now, to show that infimum of a set is equal to infimum of another set, you just use the anti-symmetric property of order, right? If you take two quantities and one is, if you take two quantities A and B, and if A is greater than equal to B and B is greater than equal to A, then A must be equal to B, right? So this is the general approach that that we are looking for. So first I will try to prove that, my claim is that infimum of xn plus is greater than equal to infimum of v. A proof of claim 1. So observe that xn plus is an element of v for all n belonging to the set of natural numbers, right? Why is that? because just uh, use the definition of xn plus. Xn plus is supremum of the set. I'm sorry. N running from n to infinity. So we know that xn plus is greater than equal to xn for all n greater than equal to n. Right. Just the definition of supremum of a set. Now, what we don't know if xn plus is greater than or equal to or less than x1, x2 and running up to xn minus 1. So, if xn plus is less than xk, then this index must be from one of these numbers 1, 2 up to n minus 1. Has to be, because for every other index it is greater than equal to that, right? So if this inequality is satisfied, this k must belong to 1, 2 up to n minus 1. So the set of all those terms xk's such that xk is greater than xn plus is a finite set, will be a finite set indeed, right? So that implies that xn plus is less than xn for at most a finite number of n indexes, right? So which implies that xn plus is a term of capital V. Since capital N was arbitrary, so this is valid for all capital N belonging to the set of natural numbers. So this is nothing but xn plus this set. I mean the sequence xn plus or the set, it will be a subset of capital V. So if this is a subset of capital V, then infimum of xn plus must be greater than equal to infimum of V. Right? So this is the first result. Now my second claim is that infimum of V is greater than equal to infimum of xn plus. This might take a while. Now see, if V is any arbitrary element of capital V, then V is less than xn for at most a finite number of n. But yeah, for at most finite number of n. Then let k, and we know that every finite set has its supremum and infimum, which are basically the maximum and minimum of that set. It always, I mean, the maximum and minimum always belong to every finite set. So let k denote the greatest index for which this inequality is satisfied. Obviously, you could find such a k, right? Because this was a finite set. I mean, all those n's, small n's, for which this inequality is satisfied is a finite set. So the maximum of that set is essentially k. I mean, the greatest index for which this is inequality is satisfied is nothing but the maximum of that set. So that implies that v is greater than equal to xn for all n greater than equal to k plus 1, right? So that implies that v is greater than equal to x k plus 1 plus is this supremum of xn and running from k plus 1 to infinity. Right, because this thing is, yeah, because v would be an upper bound for this set xn and from k plus 1 to infinity. That implies that v would be greater than equal to infimum of xn plus. I mean, since for every arbitrary v, small v, you could always find the index k plus 1 such that v is greater than equal to xk plus 1 plus, then we know that infimum of this xn plus is always greater than xk plus 1 plus. So this result is valid. So that implies that v, since v was arbitrary, what we have shown is that v is an upper bound I'm sorry. Since v was arbitrary, we have shown that infimum of xn plus is a lower bound for capital V, which means that infimum of V must be greater than equal to infimum of xn plus. So this is 2, and from 1 and 2 we could conclude that both these infimums are indeed equal. So this definition given in Bartle is also valid, which we wanted to prove. So that's it. Thank you.